Okay, I don't think it should be any surprise to anybody in the room that the automotive industry is undergoing a rapid period of evolution, whether we're talking about the march to autonomous vehicles, marching from L2 to L3 driver assist, all the way up to full autonomous L5. Electrified cars, the proliferation of EVs, especially when you look at what's happening in China in particular. Connected cars, not only your cell phones connecting to vehicles, but also cars connecting to other vehicles and vehicles to infrastructure. And then shared services, so the cars are effectively becoming hubs of applications that we spend a lot of time in our cars, and so we enjoy those applications. And what we're seeing too is that these kinds of advances and innovations are driving an evolution of the architectures that drive or process the data for those products as well. So you see this migration from discrete ECUs in the car that's been sort of the classic implementation to domain type controllers and migrating to more of a zonal architecture that I'll talk a little bit more about. So in the past, you had this concept of the discrete ECUs. You had small microcontrollers, dozens of microcontrollers in the car that would control functions like your power windows, your power door locks, individual things like that. Obviously, the wiring to support all of that is pretty extensive. Today, most vehicles have a different architecture, more of a domain specific, where functions that are sort of common are grouped together. So you see things like the ADAS controller, the comfort systems in the cabin, powertrain. Those are sort of grouped together with a common gateway that communicates out to, say, the cloud. But tomorrow, there's this migration to the concept of the zonal architecture, where you have higher compute engines that are positioned in the various zones of the vehicle, managing and processing all of the sensor data that comes in from that quadrant. And so you have nowadays, especially with more advanced driver assist systems, you have radar, you have LiDAR, you have cameras. And they all require different processing elements and a lot of processing to be able to manage and perform that sensor fusion. And so that introduces a lot of opportunities, especially for processor IP suppliers and SoC vendors, but it also introduces some challenges. Because there is a lot more diversity in terms of the types of processing that's required, that introduces a new challenge. So whether you have neural processing engines, you have vector DSPs, you have traditional multi-core CPUs, all of those things are usually integrated into a larger SoC or maybe multiple chiplets. And so the complexity is certainly higher. And as well as the amount of processing that's required to manage all of that data is certainly increasing rapidly. You also have increased security and safety. So safety obviously has been at the heart of everything that's automotive, but because there are more autonomous driving aspects or driver assist aspects, a lot of functions that were safety, say ASIL B level, more passive safety elements in the past, are now becoming ASIL D required, the highest level of safety requirements, because there's a lot more autonomy to the vehicles themselves. So your anti-lock braking system, your adaptive cruise control, these things are now become safety critical to protect the passengers and the driver in the vehicle. And so the safety requirements are increased. Security as well. So you look at these connected cars, now there are more advanced attack vectors that can be used to exploit those vehicles. And so you see the advent of, say, ISO 21434 as a standard to basically mirror the V diagram, if you will, on the development and the verification of security as a systematic requirement for development, just like it is on the ISO 26262 safety side. But you still have to have the ability to innovate around software. We look at this software-defined vehicle structure, and the ability to innovate is still a requirement. So RISC-V is a scalable, extendable standard. Scalable is important in the automotive space because it's nice that you have a single ISA that can scale across all vehicle applications, whether it's small microcontroller controlling, say, body electronics, all the way up to the more advanced ADAS systems. You have a single ISA that effectively can be used for all of those architectures. That also helps on the software development. So software components can be deployed across a wide range of vehicle architectures, whether you're more on the sort of older style discrete ECUs, all the way up to more zonal controllers. You effectively can leverage the software in multiple aspects with multiple vehicle architectures. And very important, and this is super important to us at Synopsys when we develop our automotive IP, is the ability to extend the standard. It's great that the open standard ISA helps build optimized software, but those solutions typically will need extensions, especially around real-time systems. That's what we've found, is that there are some aspects that, in order to maintain that determinism and that reduce that latency, that some extensions are required to be added to the cores. So looking at the concept of the software-defined vehicle, this sort of captures some of the elements that I've been talking about. Not only the diverse types of processing that's required, so you have your neural processing engines, you have your vector DSP, you have your dedicated safety manager, you have your security engines, as well as you have your sort of classic multi-core CPU. This also introduces the concept of virtualization. You've heard a couple of different speakers today talk about the virtualization and the importance there. This is definitely a key part of the concept of the software-defined vehicle on many aspects, and I'll talk a little bit more in detail about it, but effectively this idea that you have a hypervisor that can separate the non-safety from the safety-critical applications, all sharing the same hardware resources, is an important aspect of the virtualization concept. So I think you heard enough about what real-time virtualization is, but a couple of the key aspects of where it's advantageous, as you, I'm sure, are well aware if you've been developing around automotive, is that the certification process is very extensive, very time-consuming, and very expensive. And so having to recertify the entire system is obviously not in the best interest of getting to market. And so having the ability to parallel develop different aspects of the system, and if you make modifications or enhancements in one area, you don't have to retest everything. You can effectively focus on the parts that you're revalidating, the parts that you've modified. And then this concept of mixed criticality that I alluded to is you have to have the ability to run non-safety critical applications, say you're running an infotainment application on Linux, in parallel with real-time or safety critical real-time applications running on, say, an AUTOSAR RTOS. And those have to be run in parallel, sharing some of the hardware resources, and that's what real-time virtualization enables. And we're seeing that more and more in sort of more advanced automotive architectures. So certainly the RISC-V standard itself supports lots of aspects of virtualization. So the H extension for hypervisor support, including virtualized core local peripherals, timers, interrupts, things like that. You have memory-related virtualization aspects. The hypervisor gets physical memory protection. You have virtual supervisor physical memory protection. And then you have the interrupt architecture itself, the APLIC, or Advanced Platform Level Interrupt Controller. And this is one of the areas where we've particularly seen a need to add some extensions and some enhancements, especially around real-time systems where determinism and low latency is very important. And so the extensibility that RISC-V allows and enables is important, so that suppliers like ourselves can leverage our expertise in the years that we've been developing safety-related processors to build specialized automotive solutions that our customers demand. In terms of our products, again, we've been building automotive safety-specific cores for decades effectively. We're leveraging that expertise and experience in our RISC-V portfolio, whether we're talking about our embedded cores, our real-time cores, or our more sort of traditional host processors. Everything that we do is built around our QMS, ISO 9001 certified QMS flow, whether it's even consumer or automotive grade. But we build on top of that functional safety features into the cores to meet the random requirements of ISO 26262. And now we're extending that to the systematic requirements of security defined by ISO 21434. So at Synopsys, we're convinced that the future of automotive is built on RISC-V. We're heavily investing in the area with our RISC-V portfolio. We see that the RISC-V ISA scales across the vehicle, simplifying both the hardware and the software development. It's extendable, as I talked about, being able to add custom extensions and leverage our expertise in the automotive space to build the custom solutions our customers demand. And then the ecosystem. The RISC-V ecosystem, obviously, you look out every year, you see more and more suppliers, tool vendors, software vendors, whatnot, building out RISC-V supported tools and software. And this is basically what will drive the success of RISC-V in automotive. It enables the technology and expertise for our customers and our customers' customers to be able to develop their applications and run their software. All right, so in summary, Synopsys is very heavily invested in RISC-V across the board. There's lots of different demos, other talks, poster sessions, so feel free to attend any or all of these, and feel free to stop by our booth if you have any questions about what's going on around RISC-V at Synopsys. Thank you.